Hello everyone, and welcome to the last of the Physics 425 videos. What we've been thinking about recently is the equation of motion for a superfluid, and that has been reproduced here. The way it was obtained, if you remember, was by first postulating a wave function for the condensate in a system of identical bosons. We then took that wave function and substituted into the time-dependent Schrodinger equation. When we analyzed that equation, what we found was a complex equation. So there was real and imaginary parts on both the left and right-hand side. The equation of motion came from the real parts of this equation. Of course, Schrodinger's equation is a statement about energy. To get an equation of motion that involves forces, we then took the gradient of the real parts, and this is where we ended up. On the left-hand side of this equation of motion is kind of a representation of the acceleration of the superfluid, and on the right-hand side is the gradient of the chemical potential. But what we discovered is that the chemical potential acts as the potential energy, and so the gradient of mu is like a gradient of a potential energy, which is the force. What we want to do today is three things. The first thing we're going to do is we're going to try to interpret this derivative where we have some function f and we have a time derivative, and then we add to that velocity dotted with the del operator acting on f again. So we want to interpret what this derivative really means. It's often called the material derivative. Okay, and so the first thing we'll do is think about this through and examining a particular example. The next thing we'll do, part two, will be to try to evaluate the gradient of mu. And the reason we want to do that is because the gradient of mu appears on the right-hand side of our equation of motion. So if we can come up with some kind of insightful expression for the gradient of mu, we can then put it back into our equation of motion and see what happens. What will happen is we'll be able to understand the so-called thermomechanical effect in helium-2, or a bath of liquid helium that's been cooled below the superfluid transition temperature. In particular, what we hope to be able to do is to explain the fountain effect demonstration that we saw in an earlier video. Okay, so let's begin, and we'll start with part one, which is interpreting the material derivative. So the material derivative of a function f is, often the material derivative for shorthand is written by capital DF divided by capital DT, and its definition is a time derivative, a partial derivative of f with respect to time, plus this v dot gradient of f. Now, in our case, when we are thinking about our equation of motion of the superfluid, what we have is, instead of a scalar function f, we have the vector vs. So we're actually taking a material derivative of a velocity. And so on the right-hand side of our equation, we have dv dt plus v dot grad of v. So if you replace f with the vector v, then that appears in our equation of motion. Okay, so to understand this, let's think about the following scenario. So we're going to have a pipe, and it's going to be filled with some fluid. So we're going to imagine a fluid in a pipe. And let's initially think of this fluid as being at rest. And so now, just to be clear, This doesn't have anything to do with superfluids. It could be water in a pipe, so just any kind of conventional fluid inside a pipe. What we'll do is we'll label this as the x-axis, so x increases from left to right, and we're going to set the temperature of the two ends of the pipe. So maybe on the left end we have temperature T, and on the right end we have temperature T plus delta T. And so that means that there is a temperature gradient along this pipe, and so temperature is increasing along positive x, and so we have a positive temperature gradient. So let's imagine some little small volume of fluid inside this pipe, and we're going to call this thing a fluid particle. Just for convenience sake. Of course, if we have some finite volume of the fluid, it's made up of a bunch of individual atoms or molecules depending on what the fluid is. But let's just call this little volume element a fluid particle. So it's a volume element of the fluid. Okay, so we have this pipe and the fluid's at rest. Just to write this down in words, there is a temperature gradient along the length of the pipe. But for now, let's assume that this that the temperature at the two ends, even though they're different, let's imagine that they're fixed, so they're not changing in time. Oh, sorry. Pressed a button I didn't want to press. If the temperature at the ends of the pipe are constant, then what we would say is that the dt, so the derivative of the temperature with respect to time, is equal to 0 for our fluid particle. Okay, so in what we've imagined so far, the temperature of the entire fluid is fixed in time, although there's a gradient from left to right. And our fluid's not moving, so it's sitting, the fluid particle we're thinking about is sitting stationary, and so it's at some fixed temperature. Okay, so now what we do is we imagine that we can heat one end of the pipe. Can heat, it doesn't matter, let's say the right end of the pipe. Okay, and so that means there's still like a temperature gradient. Temperature's changing with position along the pipe, but now it's also changing in time, so that even if we have our fluid particle at rest, its temperature will be changing with time because we're changing the temperature at one of the ends of the pipe. Okay, so we heat the right end of the pipe while the fluid remains at rest. Okay, so then the time derivative of the temperature of our fluid particle is not equal to 0. So this dt is non-zero due to the instantaneous rate of change of the temperature at the location of the fluid particle. Right, and so, I mean, there's nothing surprising about that. If we have a stationary fluid and then we start changing the temperature at one of the ends of the pipe, then of course the temperature of the fluid particle is going to change. Going back to our material derivative, if F represents temperature, so if F was capital T, then scenario 1 that we've just described is really describing this term in the material derivative. The more interesting term, or the more unfamiliar one at least, is the second term, and so that's what we want to think about next. Okay, so 2. So we now return to fixed temperatures. So that means T at the left end of the pipe is fixed, and T plus delta T at the right end is fixed. But now we allow the fluid to flow. But now the fluid flows along the positive x direction. Okay, and so, for example, we could think of our fluid flowing in this direction. Now, you can immediately see that even though the two ends of the pipe's temperature are fixed in time, there is still a temperature gradient along the length of the pipe. And so now if we move our fluid particle to a new location, of course its temperature is going to change. Okay, and so we want to be able to describe that. Okay, so in this case, the temperature of our fluid particle changes because it moves to a location in the pipe that has a different temperature. So how much is its temperature going to change? Well, we take the amount that the particle has moved, the distance that it's moved, and multiply it by the known temperature gradient, and that would tell us what the temperature change is. So if we wanted to know, for example, well, okay, what's the time rate of change of the temperature? We divide by delta t, and so we'd have delta x over delta t times dt dx. But of course the change in position divided by the change in time is just the speed with which the particle moves along the x direction, and so we have vx dt dt. Now we've thought of only a one-dimensional problem, but we could have say a cube filled with water, and then we pick a fluid particle within that cube, and then there's some complicated temperature gradient that goes in some arbitrary direction, and we would have terms like this for the x, y, and z directions, and in general what we would find is that the time rate of change of the temperature of the fluid particle due to its motion would be given by this expression. And so that's exactly the second term in our material derivative. If, for example, F represented temperature. Okay, and then of course what you could have is you could have both if we were to change both the temperature at the end of the pipes with time, and we allowed the fluid particle to be moving, then we'd have both of these effects simultaneously, and the total change in the temperature with respect to time would be given by both of those terms. So if we had dt at the ends of the pipes non-zero, and the fluid particle was moving, then we would have that, let's see, the delta t dt would be equal to, well, we would have our first term would just be the instantaneous time rate of change at the position of the particle. And then we would have our Vx times the temperature gradient. Well, okay, so this would be at the position, the initial position of fluid. Okay, so and then in general, if that's the 1D case, and so in general, we would have the material derivative of the temperature would be the partial derivative at the position, instantaneous position of the particle, times this gradient term. But now in our case, in our current example, we're thinking of temperature. Okay, so for the superfluid equation of motion, we have the similar sort of idea. We had the material derivative was given by this expression, and then we had on the right-hand side our force written as the gradient of a potential energy. And so now we could, if we wanted to, write this as the shorthand notation of the material derivative. Okay, good. And so that's supposed to be a little bit of an intuitive, or at least a helpful understanding of what this material derivative actually represents. Okay, so next we want to go to part 2 of what we were planning to do, and we're going to try to find an expression for the gradient of the chemical potential which appears in the equation of motion. And to do that, what we're going to do is we're going to remind ourselves first of some things about the Gibbs free energy and how it relates to the chemical potential. Okay, so Gibbs free energy has a symbol G, and it's defined to be the internal energy minus T times the entropy plus PV. Now I've written the entropy in a funny way. I've written entropy as capital sigma, and the reason that I've done that is because we've used S recently as the phase in our wave function for the superfluid. And so I want to distinguish between those two things now. Okay, good. So if I was to take a differential of the Gibbs free energy, I would get du minus T d sigma minus sigma dt plus P dV plus V dP. Okay, and du from the first law of thermodynamics is, usually we'd say TdS, but now we say T d sigma is the heat, dq, and then we have minus P dV is the mechanical work, and then we had plus mu dN is the chemical work. So this is all du, and then we still have minus T d sigma minus sigma dt plus P dV plus V dP. And so there should be some cancellations here. So P dV cancels, T d sigma cancels, and so we have 3 terms remaining. And so therefore our dg could be written as mu dN minus sigma dt plus V dP. I'm going to need to give myself another page. Okay. So what can we do from this? Well, we can recognize that the chemical potential mu could be written as dg dN provided temperature and pressure were constant. While we're at it, we could just write down a couple of the other relations. This chemical potential one is going to be the important one that we're going to use, but we could express entropy as, let's see, minus dg dt if we had constant particle number and constant pressure, and we could express volume as dg dP for constant constant temperature and particle number. Okay. So now let's note the following. G is a system energy. Right, all of these free energies like Helmholtz free energy, Gibbs free energy, well, the internal energy of the system, they all should scale with the number of particles in your system. So the Gibbs free energy must be an extensive quantity, and that just means that it must scale with the system size. Okay, or G is proportional to the number of particles. And so if G is proportional to the number of particles, that means that we should be able to write G as being equal to the number of particles times some other function, right? That's what being proportional to n means. And this function would be, some function of whatever, some other thermodynamic quantities, temperature, pressure, and so on. Okay, so that means if I was to write down mu as the derivative of the Gibbs free energy with respect to particle number at constant temperature and pressure, then, well, n only appears as a coefficient in front of f, so if I take that derivative, I just get f. So whatever this function is. And what that also implies is that, well, sorry, let me think. Oh, yeah, I got it. So we see here now that mu, the chemical potential, by this logic, is just equal to F. And so if G is N times F, and F is the chemical potential, then we could write that G is N times the chemical potential. And so what we've worked out is that mu is equal to this function F, which furthermore implies that the Gibbs free energy, which is N times F, is also N times the chemical potential. And so this is one of our important results, is that this Gibbs free energy is just the number of particles in the system times the chemical potential. Or, in other words, the chemical potential is the Gibbs free energy per particle. Okay. So, for a system of fixed particle number, so n is constant, dg, so g is n times mu, but n is a constant, and so that means dg is n d mu. But then we also go look at dg here. It had three terms, mu dn minus sigma dt plus v dp. But we're going to say for a system of fixed particle number, then dn is 0, and dg is just minus sigma dt plus v dp. And so this is also equal to minus sigma dt plus v dp. Okay, so let's imagine what we really want to get at is a gradient of the chemical potential, because that's in our equation of motion for the superfluid. And so a gradient is a position derivative. And so let's think about like a d mu dx. So d mu dx, if we think about dividing by dx, let's also divide by n at the same time. That's going to be equal to minus sigma divided by n, and then dt we have to divide by dx. So in general, maybe this is going to be a partial derivative of temperature, depends on the other position coordinates as well. And so then we have plus v over n, and then we'd have dp dx. V over n is the same as 1 over the number density of particles. And so what we have is d mu dx is equal to minus the entropy divided by n dt dx plus 1 over the number density dp dx. We could do something similar for the y and z coordinates. And so if we did that, we'd have expressions for d mu dx, d mu dy, d mu dz that would all be of this form. And so we could write down then the gradient of the chemical potential would be equal to minus sigma over n times the gradient of temperature plus 1 over n times the gradient of the pressure. And so this was one of our goals for today, was to get this gradient of the chemical potential. Okay, so we want to use that now. So the third goal for today was to talk about this thermomechanical effect in helium-2. So what we're going to do is we're going to sub our expression for the gradient of the chemical potential into the superfluid equation of motion. I mean, you could probably already see why it's called a thermomechanical effect, because if we look at this gradient of the chemical potential, which remember is like a force equation, then, you know, it involves a gradient of temperature, so that's the thermo part, and then it involves a gradient of pressure. So if you apply pressure to a fluid, it's going to start moving, and so that mechanical motion is related to the gradient of the pressure. So, subbing into our equation of motion, we would have our material derivative, which has this form. And so that's really the acceleration of the superfluid, is minus 1 over m4 times the gradient of mu. And so now we sub in our gradient of mu. It's sigma over n gradient of t with a minus sign. And so the minus sign cancels because we have one in our equation of motion. So we have sigma n m4 times the gradient of t. And then the next term is 1 over n, the number density, times the gradient of p. So this time we'll pick up a minus sign. 1 over n m4 gradient of p. Okay, so if we have the number of particles times the mass of a helium-4 atom, that's equal to the total mass in our system, and the total mass could be written as density times the volume of the system. Okay, where the density rho is equal to the total density, which includes both the normal fluid particles and the superfluid particles in the two-fluid model. And so rho here represents the total density, because n times the mass of a helium atom has to represent the total mass of our system. And so this is the normal fluid density, and this is the superfluid density. Okay, n times m4 is equal to the number of particles times m4 over the volume. And so that's just the total mass divided by the volume, and so it's just rho. So bringing all of this together then, what we have is dvs dt plus vs dot del acting on vs is equal to sigma over rho v times the gradient of temperature minus 1 over rho gradient of the pressure. Okay, and so this is what we're going to try to use to interpret this thermomechanical effect and ultimately the fountain effect. So this is the thermomechanical effect. So it's I think the simplest way to interpret this equation is to just recognize that on the left-hand side, what we have is the acceleration of the superfluid. And so on the right-hand side, we have gradients of two thermodynamic variables. And so let's suppose we kept the pressure constant, no pressure gradient, but then we have a temperature gradient. Then that's going to cause the superfluid to accelerate. we could also have a uniform temperature and then apply a pressure gradient, and that is likewise going to cause an acceleration of the superfluid. Okay, so temperature gradients and pressure gradients. Temperature and pressure gradients both cause an acceleration of the superfluid. I have to keep adding pages here. Okay, good. All right, so let's think about the equilibrium case when the superfluid is at rest. Or, sorry, it doesn't have to be at rest. Imagine the superfluid velocity is constant, so it's not accelerating. So in equilibrium, Vs is constant, and what we would have then is, well, from our equation of motion, we'd have 0 on the left-hand side is equal to sigma over rho v gradient in temperature minus 1 over rho gradient in the pressure. And so what we can do, I think, is cancel the density on both sides. And what this would really tell us is that how the temperature and pressure change are related. So delta P over delta T. So let's see, we bring the gradient in the pressure over to the left-hand side, then we would divide by the temperature derivative, and so we would have sigma over V. So that's the ratio of the entropy and the volume of our helium-2. So remember, the superfluid has no entropy, and so the entropy is due to the normal fluid fraction. This is known as the London equation. Okay, so now let's think of an experimental setup here. So we're going to start with a set of parallel and linked test tubes. Let me try to I want to just make them look the same as much as possible, so we get a little bit fatter. Okay, and so this is going to be side A, this is going to be side B, and initially they're filled with helium-2 to the same level. And what we have to know about this link between A and B is that it's a super leak. And so that means there's like a fine powder that's been packed into this narrow channel. And what that fine powder does is it makes these kind of microscopic capillaries. Only the superfluid can pass through these fine capillaries. The normal fluid can't pass through. Okay, so the idea is that the system is filled with helium-2, and so the total density is determined from the sum of the normal fluid and superfluid densities. We're going to start with the two sides at the same temperature, and we have equal proportions of rho n and rho s on each side. And so also the levels are the same on both sides. And so let's just be clear about this super leak. This is does not allow normal fluid to pass through. Normal fluid cannot pass through. Only superfluid can pass through. When we saw the video of the fountain effect, what they described as using something called jeweler's rouge as the fine powder that they tightly packed into this narrow channel. Okay, so one thing we want to remind ourselves of is this plot of the superfluid and normal fluid density as a function of temperature. So at high temperatures, what we have is all normal fluid, and so this is rho n. So the entire density is made up of normal fluid. And then we go through the superfluid transition, and the normal fluid fraction decreases, and then it goes to 0 at really low temperatures. On the other hand, the superfluid fraction is basically all superfluid at the lowest temperatures, and then as we go higher in temperature, we go through this transition, and then the superfluid fraction vanishes above the transition temperature. Okay, and so maybe we imagine that we start with our system in these parallel and connected test tubes at a certain temperature, and so it doesn't matter what temperature we pick, but we pick one. And so this is, say, our initial temperature T0, and that means on both sides of our test tubes, we know what the normal fluid density and the superfluid density are, and they're the same on both sides. Okay, so next, we now apply pressure to side A. Okay, and so let's draw our test tubes. And so there it is. Inside here is our super leak. We apply pressure to side A, and so its level decreases. The normal fluid can't pass through the super leak, and so that means that only the superfluid passes through the super leak, and so what we end up with is here's TA and PA, and here is pressure B is less than pressure A because we're pushing on side A, and there's now a height difference, and this height difference is proportional to the pressure difference that we applied. And so here's the high pressure side, and here's the low pressure side. So I want to think about this plot over here. We have pushed superfluid out of side A. So now side A has more normal fluid than superfluid. And so if we wanted to increase the amount of normal fluid, then we would move along this curve in this direction. And so here's side A at temperature TA. It's lost superfluid because it's gone through the super leak, and therefore the proportion of normal fluid has increased. On the other hand, we've pushed more of the superfluid into side B, and so it had to increase the amount of superfluid density, and its temperature would therefore, according to this plot, have to decrease. And so it's lost, the proportion of normal fluid is decreased, and the only way that can happen is TB is decreased. And so what's happened here is we have a pressure gradient, and the pressure gradient points from low pressure to high pressure, so it points from side B to side A, and the superfluid flow is in the opposite direction. And so we could go look at that. Does that make sense in our equation of motion? And it does. If we focus on the gradient of the pressure, there's a minus sign here, which says that the superfluid acceleration is in the opposite direction of the pressure gradient. And so that all seems to make sense in this example. What happens, though, is that what we found is that there is a temperature gradient that's going to develop. The temperature gradient pointing from the low temperature to the high temperature is going to point from B to A, and so we end up with a, sorry, probably, let's change back to black, and so we would have a temperature gradient develops as the superfluid flows. And what tends to happen if we go back to our equation of motion, when that temperature gradient develops, it tends to accelerate the superfluid in the same direction as the temperature gradient. And so that would cause tend to cause the superfluid to want to flow in the other direction. And what happens is that the temperature gradient and pressure gradient balance until they become equal to one another, and the acceleration of the superfluid stops. Okay. So what we can say is that from equation star, if we start with a uniform temperature and apply a pressure gradient, we get superfluid flow in the opposite direction of the gradient of P. This flow continues until the temperature gradient that develops balances the pressure gradient term, or until the temperature difference is equal to V over the entropy times the pressure difference from the London equation. Okay, and people have done these experiments. And so here is an analogous setup where what they have is kind of like an inverted beaker with an opening at the bottom, dipped into helium-2, and then what they do is, instead of applying a pressure, what they did is they turned on a heater to increase the temperature inside the beaker. The superfluid flows in the direction of the temperature gradient, and so it tends to fill up this beaker, which causes a delta H. Let's see. Should be a delta H. A delta H to develop, which corresponds to this pressure difference, until an equilibrium is established. And so, okay, and so they've done this for helium-2 at a bunch of different temperatures. So here's 1.3, 1.5, 1.6, 1.75, 2 Kelvin. And what they did is they measured and plotted how delta T and delta H are related, and the slopes of these lines, right? If we look at our delta T versus delta P expression, the slopes of the lines can be used to determine the entropy of the helium-2 at different temperatures. Okay, good. So I have one more thing to show you. We can do something more similar to what they did in this experiment. And so let's now consider the inverse experiment. So we're going to start with no pressure gradient, and we're going to heat the helium-2 in side A of our setup. So here are our parallel test tubes. Our super leak is in here. And we're going to imagine maybe feeding a resistor through, and so that if we pass a current through our resistor, we can heat the left-hand side, the left test tube. You could also just have a little ball of powder in there and shine a laser pointer onto that ball of powder or something like that. Okay, so that means, let's see, temperature TA is going to be greater than temperature TB. And so what's going to happen is we'll get a temperature gradient that points from the low to high temperature. And from our equation of motion, we know that the acceleration of the superfluid is in the direction of the temperature gradient. And so we'll have superfluid flowing from tube B to tube A. Okay, so with the gradient of P initially equal to 0, we'll start, when we apply this temperature difference, with an acceleration of the superfluid determined from this expression of entropy over rho v times the gradient of T. So the superfluid accelerates in the direction of the gradient of T, so towards high temperature. So remember, there's another law of thermodynamics which says that heat should not flow from a cool temperature to a warmer temperature. Entropy is related to heat, dq is TdS, and so that's one of the ways in which people determine that the superfluid must not carry any entropy. So this flow continues until, again, we reach this equilibrium condition where the pressure difference that develops offsets the temperature difference. Now, if you have an open beaker where the height difference that gets established, you can't get to the delta H required to get equilibrium, then what you'll have is superfluid helium flying out of this spout, and so this is the fountain effect. And so just to try to be clear here, down in here is where you're going to have your packed powder. Powder. And here is their heater. This is the level of the superfluid that's outside this kind of little beaker that's been submerged in. And then, of course, you can see the fountain spraying out the top. Okay, good. So that's where I'm going to stop. Thank you very much, and I will talk to you again.